learned at the last lecture? What we learned the last lecture? Anybody who can answer what we learned the last lecture? Huh? Simple harmonic motion. Okay. Simple harmonic motion. And what other things that we learned in the last lecture? You can pick up one word if you like. Huh? Okay, 3 response. That's good. What other things we learned last lecture? Natural frequency. I like to hear that. Natural frequency. Okay. And critical damping. Ah, it's getting better and better. Damping. Okay. Well, there's damping ratio. Okay. Damping ratio. Damping ratio essentially sees the damping with respect to critical damping. You want to compare his value with respect to critical damping. And that is the ratio. The ratio is very important engineering measure. So you may compare your handsomeness with this critical handsomeness, right? Then if zeta is greater than 1 or less than 1 or equal to 1, that's the ratio, right? Okay, ratio. Percentage. Usually this is expressed in terms of percentage. Okay. For example, when we have simple oscillator, some students have the critical damping, the damping ratio of this is very small. If damping ratio is 1, then how does it behave? Then push, come back, and stop, right? That's the critical. Okay. I think you guys pick up to what we learned during the last lecture. Okay. Actually, we learned the free vibration, free response is governed by the following governing equation. Governing equation. This we call governing equation. 0 means free vibration. Free from external excitation. And the solution mathematical solution, as I am saying, was expressed, if I denote x is the displacement from, measured from the equilibrium position of the mass, toward downward, then we found that this can be expressed as x exponentially decaying term, and A1 exponential plus J Okay, how did you find this? We solved this, right? And also assuming that xt can be expressed, and these are 2 lambda 1 and lambda 2, right? And then using the window that is described in the text, we all agree that we can write this and the phi is the phase angle that is determined by the initial value, because when t equals 0, this is 0. So sine phi, and this is 1, so A sine phi is x0. Right? So we can get the phase from initial condition. So phi is a function of initial condition. And especially we call this omega d, damped natural frequency. And noting that zeta is always less than 1, therefore square root 1 minus zeta squared omega n is always less than omega n. Therefore, damped natural frequency is slightly smaller than natural frequency. Okay, typical zeta, for example, still 5. Typical zeta of still 5. It's like less than 1%. So that is 0.01. So if I square that, then that is 10 to the minus 4. 1 minus 10 to the minus 4. It's like subtracting 1 from 10,001. Manon minus 1 is Manon, right? So almost Manon. The 10 to the minus 4 is pretty negligible. So usually damped natural frequency is approximately the same as natural frequency. But strictly speaking, it's a function of zeta. Square root 1 minus zeta squared. Okay. So when we measure natural frequency, what we actually measure is omega d, not omega n. Right? So to measure omega n, precisely we have to measure zeta first. Okay? And in the last lecture, we thought about how to measure zeta, and I said you will learn the way to measure zeta later on in this way. Okay, we will go over there. That is a C over CR. The CR is 2 square root